Hello everyone, I'm going to present our recent work, Security Proof of Practical Quantum Key Distribution with Detecting Efficiency Mismatch. This is a joint work with Patrick, Adam, Jie, and Norbert. I started working on this problem when I was at IQC Waterloo. First, let me motivate why we study efficiency mismatch. The first reason is that efficiency mismatch always exists in practice. Suppose we would like to measure the polarization state of a single photon. We need two detectors and one polarizing beam splitter. Due to fabrication, it is difficult to make these two detectors have the same efficiency. Also, the coupling efficiencies of these two detectors may depend on the alignment and setup. The second reason is that besides polarization, photons have multiple degrees of freedoms. A detector may respond to a photon differently depending on these additional degrees of freedoms. People have observed spatial mode dependent or temporal mode dependent efficiency mismatch. If Eve can access these additional degrees of freedoms, Eve can effectively control efficiency mismatch. This will help Eve to attack QKD system. Actually, people have demonstrated such attack in experiment. Suppose Eve can fully control efficiency mismatch, then Eve can perform a perfect intercept and recent attack. In this case, Eve will learn every possible result of Bob, so it is impossible for Alice and Bob to share secret keys. Another problem caused by efficiency mismatch is that with efficiency mismatch, detection events are not fair samples. So if we perform a verification task, such as entanglement verification, we can get false positive results if we only use detection events. For example, people have demonstrated with efficiency mismatch, we can see a fake violation of a Bell inequality, even if the state is classical. In this work, we will study the effect of efficiency mismatch on security proof. For this, we just study a simple QKD protocol, prepare measure BB84 protocol. According to this protocol, at each round, Alice prepare a single photon polarization state. The polarization is randomly selected from 4 possible choices. After this, Alice will send the single photon via a public channel to Bob. When the optical signal is received by Bob, Bob will perform corresponding measurements. It turns out there is an equivalent description of this process. That is, instead, Alice can access an entangled photon pair source. Alice will keep one photon and send the other photon via public channel to Bob. Alice can prepare the state of the photon to Bob by performing proper measurements on her photon. Since Alice lab is secure, from outside of Alice lab, it is impossible to tell which scheme, prepare measurement scheme, or entanglement-based scheme is implemented. For our security analysis, we will use the entanglement-based scheme because, as you will see later, we formulate the security proof as an optimization problem on the state shared between Alice and Bob. I also would like to mention because the entanglement-based scheme is a hypothetical description. In our analysis, we will assume Alice measurements are perfect with ideal detectors. One warning is that the system sent out by Alice is a single photon. However, the system received by Bob may be infinite dimensional because over the transmission, Eve can replace the single photon by optical pulse. In this work, we will study efficiency mismatch in Bob's measurement. So next, let's see how Bob performs measurements. Bob can use either active detection scheme or passive detection scheme. In the active detection scheme, Bob will use one random bit to control the polarization rotator in order to choose different measurement bases. In the passive detection scheme, there is a 50-50 beam splitter depending on which output arm. So either the HV basis or DA basis measurement is performed. In the active detection scheme, there are two detectors. We will study efficiency mismatch between these two detectors. Also, the mismatch may depend on the mode of the incoming signals. So we will study this kind of mode-dependent efficiency mismatch. Similarly, for passive detection scheme, we will study this kind of mode-dependent efficiency mismatch. In this work, we will illustrate our method with these two special mismatch models. However, I would like to emphasize our method works for arbitrary efficiency mismatch as long as this match can be characterized. Before going to the details of our method, let me first review the current status. In order to handle infinite dimensional system, when there is no mismatch, people usually apply a Gaussian model. With a Gaussian model, we can map multi-photon state to single photon states. So effectively, the Bob's system is a qubit. Hence, standard security proofs with qubit assumption apply. However, with efficiency mismatch, the above Gaussian model doesn't work anymore, so it is an open problem to prove security with efficiency mismatch. Previously, there are several works for security proofs with efficiency mismatch. However, all these works make additional assumption on the system of Bob. That is, Bob can receive at most one photon at each round. However, in practice, Bob performs measurements with threshold detectors. It is impossible for Bob to tell whether this assumption is satisfied. In this work, we will develop a method to handle the infinite dimensional system. By the way, I would like to mention, in parallel with us, recently, Turchachin also developed another method to handle the same problem. So now let me introduce our method. Our method is based on a numerical formulation of a security proof. So first, let me introduce this formulation. We can think a general QKD protocol as follows. There are several steps. The first step, Alice and Bob try to share entanglement. Then Alice and Bob perform measurements. Alice and Bob can repeat this process multiple times. Then they can get correlated classical data. After this step, they will do post-selection, which includes announcement, safety, and key map. Finally, they will share raw case. It turns out each step described here can be formulated as an operation or constraints on the state rho AB shared between Alice and Bob. Then we can think the K rate as a function of the state. Rho AB, each possible state just corresponding to one possible attack of EU. In general, the K rate has two terms. One term is called privacy amplification. The other term is for error correction. And the error correction depends only on classical data, so we do not need to do optimization. However, the privacy amplification depends on the state shared between Alice and Bob. We can formulate an optimization problem in order to find the optimal attack of EU. It turns out The objective function to be minimized is a convex function, so we can apply numerical method to obtain both lower bound and upper bounds under QCrypt. This method has been well developed. Please see these two previous work. Here, I just would like to adopt this formulation for security proof of the protocol we study. So the first obvious problem we need to address is that Bob's system is infinite dimensional. Numerical optimization can't handle infinite dimensional system effectively. To address this problem, we introduce an artificial map called flag state squasher. By using this map, we can train infinite dimensional system to a finite dimensional system. The key observations is that each measurement operator of Bob is block diagonal in the photon-number basis. So if we choose a photon-number cutoff, we can split the whole basis into the small photon subspace and the large photon subspace. Then we can write down the POVM as a block diagonal matrix. According to the protocol, we perform such measurement on an infinite dimensional system. However, there is another description of this measurement process. In this description, there are two steps. We first apply a squasher. Depending on the photon number, we either leave the state unchanged, or if the photon number is high, according to the squasher, we just perform the measurement. Depending on the measurement results, we prepare a classical state. Since the number of measurement results of Bob is finite, so after this step, we will get a finite dimensional system. The second step of this description is just we apply a squashed measurement on a finite dimensional system. In a small photon number subspace, the squashed measurement is the same as the original measurement. However, in a large photon number subspace, we just need to perform a projection now. It is easy to see both descriptions give us the same results. In our QCrypt calculation, we just adopt the description with squasher because in this case, Bob's system is finite dimensional. However, in this description, we allow you to access this squasher. So if you can know the photon number, so you can know completely every possible result of Bob when the photon number is high. For this reason, we need to lower bound on the probability the state in a small photon number subspace. So the second step is just to find the photon number distribution. Before telling the details of this step, let me summarize our method. According to our method, we formulate a finite dimensional convex optimization problem. Also, the measurement operators of Bob depend on efficiency mismatch. Hence, we can study the effect of efficiency mismatch on QCrypt calculation. So now let me tell you the details of second step of our method. How to bound the photon number distribution. We consider an observable T. This observable may depend on the photon number, also on the potential efficiency mismatch. In our situation, the observable is block diagonal in photon number basis. So we can assume the state is also block diagonal. Then we can write down the value of the observable as a probabilistic mixture of the values of the observable depending on the photon number. So next, if we can find photon number dependent lower bounds on the observable, then we can lower bounds the overall value of the observable. In addition, if we introduce a cutoff k, and depending on whether the photon number is low or high, we introduce two different lower bounds. Also, in the small subspace, the lower bound is less than the lower bound in the large photon number subspace. Then we can rewrite this inequality to get a lower bound on the photon number distribution. That is the probability of the state in the small photon subspace. We will follow this procedure for our measurement setup with efficiency mismatch. Before that, I would like to mention similar method has been used for standard security proof without efficiency mismatch. Now let's see how this procedure, how to implement this procedure. For the active detection case, the intuition is that multiple photons will cause clicks at both detectors. We call this double clicks. With the increase of the photon number, the double click probability will increase. That's our intuition. We can formalize this intuition by studying the double click operator. Particularly for this mismatch model, I demonstrate the double click probability. It depends on the photon number. Also, you can see the double click probability monotonically increase with the photon number. We get both numerical results and analytical results. For numerical results, we just need to solve SDPs. For analytical results, recently we figure out a method which is motivated by the work of Church-Chicken. And due to this monotonic behavior, we can lower bound the photon number distribution as shown here. Similarly, we studied the passive detection scheme. For this case, the intuition is multiple photons will leave the first 50-50 beam splitter at different arms. These photons will trigger detector clicks at different bases. So we call this cross clicks. With the increase of the photon number, the cross click probability is expected to increase. So we can formalize this intuition by studying the cross click operator. For this special mismatch model, I demonstrate the dependence of the cross-click probability on the photon number. You can see this monotonic behavior. Because of this, we can lower bound the photon number distribution. Next, I will illustrate the performance of our method. For this, we use simulated data. We simulate the observations according to a simple model. In this model, at each round, Alice just prepares one of four possible polarization states according to the protocol. Then the single photon is sent out from Alice via a public channel to Bob. The channel is specified as follows. With probability T, the single photon will be transmitted. Also, the depolarization noise in the channel is omega. Also, with probability R, the single photon will be replaced by a multi-photon. So the multi-photon probability is R. When the signal arrives at Bob, Bob will perform the measurements according to the active detection or passive detection scheme. Our task is just to try to lower bound the K rate given observations and the mismatch. Before demonstrating the results, let me emphasize, we specify these channel parameters just for data simulation. However, in our security analysis, we do not require any characterization of the channel connecting Alice and Bob. That is, we do not make any assumption on Eve's attack. So now let's see the results. First, let's see the case without mismatch. Here, I would like to illustrate the different effects of trusted loss and untrusted loss. A photon can be lost over two processes. One is over the transmission from Alice to Bob. Since this transmission channel is accessible by Eve, so the loss is untrusted. Another loss is inside of Bob's lab. because Bob's lab is secure, so this loss is trusted. Here, I just fix the overall loss, and then you can see the key rate depends on the trusted loss. In general, the results shows with the increase of the trusted loss, the key rate will increase when we fix the overall loss. So next, let's see the case with efficiency mismatch. First, let's see the active detection scheme. So there are two detectors. We can study the mismatch between these two detectors. For security analysis, we can assume the system received by Bob is finite dimensional, or without such assumption, we just use a flag state squasher. Here you can see making assumptions will overestimate the key rate. Also, in general, with the increase of the efficiency mismatch, the key rate decreases. We can also consider mode-dependent efficiency mismatch. You can see mode-dependent mismatch will help you to attack the system. Similarly, we studied the passive detection case. We consider mismatch between these four detectors. For security analysis, we can either make an assumption or without such an assumption. Also, we can study mode-dependent efficiency mismatch. We obtain similar results as the active detection case. With this, I would like to conclude my talk. We constructed a flag state squasher to simplify the optimization problem. This flag state squasher is general. It can be used not only to the protocol we study, but also to other protocols. Please see the recent work at Norbert's group for these applications. In order to use flag state squasher, we also need to obtain bounds on Photon-number distribution. We derived both numerical and analytical bounds. By combining these two steps, we proved the security of BB84 protocol. In the presence of efficiency mismatch, also our security proof without assuming a Photon-number assumption, without using a Photon-number cutoff. We also demonstrate the individual effects of trusted loss and untrusted loss for key rate calculation. Finally, I would like to comment that numerical approach is a powerful method. It can be applied not only for key rate calculation, but also for finite key analysis. Please see the talk by Ian for the details. Thank you very much for your attention. If you have any questions, feel free to ask me over the online conference or email me later. Thank you. Bye.